Parents and students, hello, my name is Harim Yu, and this is an introduction to my Essential Guide to Algebra 2 course. All right, so this is one of the curriculums that I'm going over called, usually known as the Essential Math series. And I would like to explain, what consists of Algebra 2, why this is different from someone else's Algebra 2, and what makes it different from Algebra 2 and Pre-Cal and whatnot, and explaining how to take my course effectively. Right, so who takes Algebra 2 and when? Especially for this course. I have two sets of audiences for this my course. If you look at year-wise, we have grade 7 and 8 who are mathematically talented and want to learn Algebra 2 beforehand so that they can actually go on to AMC 10 and the other math competitions. But of course, there are some kids who are just taking Algebra 2 only for school preparations and GPA preparations as well. So there are twofold purposes. One of them is to make you get prepared for GPA materials, not just for like grade 9 and 10, but the other one, the additional or some kind of a bonus one, is going to be make you like a foundation, build a strong foundation for AMC 10 and 12, and of course other math competitions as well. This doesn't mean that if you take my Algebra 2 course, you're going to get prepared for AMC 10 and 12. No, that's not true. We're only giving you, the whole course is going to give you just the building blocks for the math competitions. So if you want to take some hard, challenging courses, you got to take the math competition courses. But over here, we're going to learn about all those foundational stuff. You can consider this as a vocab class. And the competition math is going to be more about writing practices. So after you learn about all the basic vocabs, there are some intermediary level vocabs and some challenging level vocabs, right? LSAT vocabs and SAT vocab and TOEFL vocabs, they're all different, right? You can consider them all same, but essentially they're not. LSAT vocabs are not coming out, in our daily lives. So that being said, we have twofold purposes. The primary goal is to make you get prepared for Algebra 2 for schoolwork. I want you to get A in the school. I want you to get A in the school. And also, if it's convenient for you, if you like how I explain things around, I want you to take the competition math as well so that you can actually start your extracurricular activities based on math. Now, lots of parents, and I think some of the parents will actually look at this video clips, and can I say you will actually get confused about how to prepare Algebra 2, when to prepare Algebra 2 for your kids, right? So I want to compare the curriculums between the South Korean curriculum and US curriculum. In Algebra 2, the course contains everything starting from middle school year 1 to year 3. So in US, it's going to be 7, 8, 9. All of them are compactly, compactly sitting inside Algebra 2, intertwined with one another. And all 3 years are in there. And you can consider this as a first semester of each year in middle school math. And we learn about polynomial math, radical functions, not all of the polynomial functions, not the hard ones you are expected to find in 수학의 정석. You're not going to see those, but there are polynomial functions, applications of polynomials, and I put some applications of polynomials that are similarly close to competition level math. So you might feel, or your child might feel, that it is a bit challenging in some topics, but in overall, it's not going to be super challenging. But there are radical functions and rational functions. They might be dealt in middle school year, but also they're going to be covered in high school year number 1 or year 2. You can call it at 10th grade or 11th grade. You guys will see those math. And of course, there's a new thing called exponential and logarithmic functions. They're not part of middle school. They're not part of just regular high school as well. It's actually part of what? 미적분, calculus in high school, in Korean high school. But that doesn't mean that we're going to learn, exponential function and logarithmic functions in detail as much as we would in 수능 수학 or the AMC math. But we're going to learn about the basic stuffs about how to graph exponential functions, how to explain exponential function stuff, all the way at least up to SAT 1 level math. And logarithmic functions are going to be dealt in Algebra 2 course. Now, basic sequences and series, there are a lot of things that I need to talk about here. In regular Algebra 2, sequences, they study only a few things. The first is arithmetic sequence, the second is geometric sequence, and sometimes they would learn different sequence, but they might not learn about the different sequence. And they do learn about series, and they normally don't learn about recursive sequences or recursions. But in my Algebra 2 course, I put arithmetic, geometric, obviously, and I put all the series that you have to know, and recursion, and different sequence, which are part of like the math competition math. And I've been explaining that in my lecture. So if you take some of my courses, it's going to be a little bit going above and beyond the regular Algebra 2 course. And that means in Korean high school or Korean school, when they learn about recursions, they won't go into details as they would in competition math in US. So I hope that this is going to be super helpful for kids who are learning it. And probability and probability distribution function is also going to be dealt quite in detail. What I'm saying is that I don't normally go into just explaining, oh, the probability is this and that. I explain things of how to approach single question using multifaceted ways so that student can actually solve it using the combination method, permutation method, or just like the rules of probability, just using the rules of multiplications and additions. This is going to be helpful. And Algebra 2 Honors includes trigonometry. This course doesn't include trigonometry in it. But that doesn't mean that I'm only covering up to Algebra 2. I go a little bit further than Algebra 2, so including portions of Algebra 2 Honors, but the trigonometry part is going to be solely included in my pre-cal. So I subdivided into two classes, things that include trigonometry and not. Okay, so if you're interested in learning trigonometry, you got to take my pre-cal course. Right. So Algebra 2 and pre-calculus. Why did I divide trigonometry into two parts? For most of you who are watching my clip right now, must have seen my prep books that are in the library, not in the library, but in like, the bookstores, right? The offline bookstores, you guys would have seen it. And for those of you who actually saw my pre-cal, you guys would notice that my pre-cal is going to be a little bit harder than the regular trigonometry. It's completely different from regular trigonometry because I designed it to prep for it. I designed it for this prep book, especially the pre-cal, for students to actually prepare for AMC 12 and HMMT and high-level math competitions as well. I gave all the foundational stuff, not just like the easy one, but the harder ones, using the complex plane, using all those complex, the Mova theorem, Euler's theorem, and all those things that are not normally covered in like in regular pre-cal or even pre-cal honors, but I put it in my prep book. So the audience who are taking my pre-cal is going to be the 10th grade and 11th grade. That's why I pulled it outside. That's why I pulled my trigonometry outside the Algebra 2, because I want my Algebra 2 solely for grade 9 and grade 10. Some kids who are taking at 7 and 8, they're fine. But kids who are entering into 11th grade, got to take pre-cal. And if you like challenging math, take pre-cal. Right, so let me talk about themes of this, the Essential Guide to Algebra 2. And I contain three major themes. Must learn core concepts in Algebra 2. What does that mean? It means that I put all the concepts that you need to learn in order for you to get A in your GPA, okay, and for your grade. And fundamental problems related to concepts in math competitions. I didn't say AMC 10 and 12. I talked about all the other math competitions as well, including like, Berkeley Math Tournament, including Rice Math Tournament, Duke Math Meet, Lehigh Math Meet. All those math competitions use these fundamental skills that you got to learn in Algebra 2. So I put all of those fundamental problems. Doesn't mean that these problems are hard. It means that I'm making you have at least a soft landing for math competitions. Now, multifaceted solutions to the problems. Sometimes it could be just like one solution. Sometimes it could be two-folded or three-folded. I included many solutions as much as possible. What I'm saying is that in order to solve one question, there's an easy route. There's a shortcut. There's always a leeway to solve that one question. But there's the fundamental way of solving it using just the core basic tools, right? So I put some of those solutions in multifaceted form so that you guys can actually enjoy solving this problem by looking at it in many different perspectives. Right, so the contents include part 1 and part 2. the part 1 talks about real number system. Real number system is also different from the regular real numbers that you would have seen or your child would have seen in any prep book or textbook, because I put I put some kind of contest level math solutions, not the problems. The problems are easy, but the solutions are not. What I'm saying is that when I explained about the real number system, I talked about the trichotomy, and especially thinking about like performing caseworks and case enumerations. And when you see the real number, when you see the phrase about the real numbers, I emphasized about the fact that kids have to perform caseworks, especially for the contest level math. And those kids who actually, like they qualify for AMY and some other math competitions, they've been saying that this was really helpful. So I put those real number system, especially in the contest level, contest level math or perspectives. And if you move on to function and linear graphs, I focused more onto SAT 1. And I put lots of similar questions that you can practice for SAT 1, especially dealing with the linear functions. And for system of equations and inequalities, I emphasize more on GPA materials. I didn't cover anything about like contest level math. I simply focused on the GPA material. So if you are having some difficulties on GPA, please, just look at the guidance and just, especially focus on some of the chapters that you feel challenged. And the fourth one, quadratic functions and factorings. This obviously comes out in contest, but I focus a little bit more on GPA materials, explaining why, there's a major differences between my quadratic equations in Algebra 1 course and Algebra 2 course, because I've been covering something about the absolute valued quadratic functions. But that doesn't mean that contest level math is not included here. I put more questions related to the GPA materials, but a little bit less for a contest. Now, if you move on to the rest of the part 1, polynomial functions, the graphing polynomial functions are pretty much the GPA materials. I gave some hints. I talked about some hints and some of the strategies that your a student has to take in order to get like really good grades in the boarding schools. But for applications of polynomials, I thought about how a student should learn about like polynomials in terms of like contest level math. So I focused more on contest level math other than GPA materials. So whenever I went over something about the rational root functions and whatnot, and a rational root theorem, and integer root theorem, the Cart's rule of signs and whatnot, I've been focusing on the tournaments, the math tournaments. So it might be going a little bit beyond the GPA materials, but it's going to be helpful for you guys. And a radical expression and functions, I simply focus on GPAs, but some of the questions are also some of the references that I made actually are related to contest. And rational expressions and functions, I gave GPA materials for it, but graphing part, I've been thinking about contest level math. So that's part 1. Now part 2 deals with exponentials and logarithms. Exponentials and logarithms, even though I said it's about the contest, I didn't focus a lot on contest. I focus a lot on GPA. Okay, so if you have to learn about the super basic stuff, please take this. And sequence and series, of course, I talked about there's SAT 1, SAT 2, but SAT 2 is gone. So I've been talking about like contest level math, but again, like school level GPA materials are all part of it. And especially I focused on different sequences, and I've been thinking about the Berkeley Math Tournament questions. In year 2015 and whatnot, there were a question related to the different sequence, and if you didn't know about the different sequence, you can't solve it. And in international schools, including like SIS and KIS and all the other international schools in South Korea right now, you guys will learn about the different sequence. So whenever you learn about it, please use the method that I'm explaining it here. And counting, well, this is my favorite part. Counting permutation and combination and probability. I tried my best to explain how, like counting deals with the multiplication symbols and the addition symbols, and try to get away from the notations. Even though my subject or the topic is called permutation and combination, I try to get away from the formula itself. I try to give you the best way to just use the basic tools of multiplication and addition to solve some questions. And I went over some circular permutations. I went over all the permutations, including the repeated letters, and like permutation allowing repetitions, combination allowing repetitions. I just touched upon it, which means those combination allowing repetitions, permutation allowing repetitions, partition of sets, partition of natural numbers, they're all going to be covered in competition level math. So if you are willing to take those courses, please take the other course. But this one is designed for school level math. So I tried my best not to talk about those hard stuff. I tried to talk about some like not so easy, but fundamentally important ideas in schoolwork. And probability, yes. I tried my best not just to focusing on combination method, because your school teacher may ask you about some questions about the arrangements of certain objects allowing repetitions. And if someone allows repetitions, you cannot use combinations. So because of that, I tried my best not to talk about combination method. I've been solely focusing on the principle of multiplication and probability. So that being said, lastly, I've been talking about probability distribution functions using calculator method and non-calculator method. So those are the two parts of Algebra 2. Suggestions, please read the booklet. You know, like you can solve the questions on your own first, but I want you to also, you know, like write down notes neatly as possible, right next to your own notes, so that as I wrote down those notes, I've been talking more than necessary. So that means that I didn't make any, you know, jokes. I didn't make any like stupid jokes. I didn't spend time like, you know, like inefficiently. I didn't spend time like talking about like stupid, silly stuff. I've been trying my best to fill all the time, the given time slot for me with the information, the contents that you need to know. Okay. So please write down the notes and remarks covered during the lecture. And that doesn't mean that you should be robotic. It means that you got to be active learner, right? So you got to think about why each concept is used in each problem. You got to think about how each concept is used there. What I want you to do is that internalizing each concept in detail into your brain cells so that you can use this in competition level math, not just in GPA materials, okay? And remember, and this is a set of building blocks for competition math. So I consider this as a foundational courses. It's like a strong foundation for AMC 10, 12, and above, right? So please, when you take my course, I did my best to explain things in detail, but I did my best also to stay in that line, okay? To stay on that line, not to cross away onto the competition level math. So I hope you enjoy this course, and if you enjoy my course, I want you to take my other courses as well, you know, like competition math or like pre-cal and so on. And I hope that I can teach you all the way up to 12th grade, so that when you go to like top college, like super, like awesome colleges, like please, you know, like remember that I walked beside you. Right? So that being said, I hope you enjoy my class, and that's it. Thank you. Hi everyone, welcome back. We shall begin with topic number 2 of algebra. All right, so relation and function. First, I gotta give you a brief snapshot of what we're about to do in this topic. First off, we will focus a lot on SAT 1 level style type of questions, especially when we have to deal with functions and linear functions, and we gotta see some word questions and whatnot. And we're gonna also go over direct variations, and also we're gonna hit some parts that are just focused on GPA related materials. But first off, we gotta understand what relation and function is. And this type of notations, the difference between relation and function, well, it has been somehow spotlighted around early 1900s. Now, before 1900s, nobody actually distinguished between relation and function, and especially for those people who already made calculus, Newton, Leibniz, Bernoulli, all those great mathematicians, They didn't distinguish what function is. They didn't distinguish what relation is. They knew that if you plug one input, they got to have one output. But the modern notation of what we use actually started to come around like 1900s. And by the way, when I say 1900s, they started to come up with a way to figure out between relation and function, which is known as vertical line test. Now, relation can have one input to multiple outputs, to many outputs. Now, function, on the other hand, that's a relation. Function is very, I guess it's very somehow like moral. What am I saying? Like, it's not even moral. Like, function has one input, goes to one output. It just doesn't have, like, it's not wishy-washy in a way. So function stays inside relation. It stays inside relation. And when we say function, it says one input goes to one output. That's all you got to know. All right, so relation and function. That being said, let's try to talk about some questions, and let's try to go on question number 1 and see what's up. All right, so what does it mean? Now, first we got to understand that 3 has been connected to -1, okay? So input is 3, output is -1. 4 is connected to 2, 5 is connected to 4, and -2 is connected to 0, 8 is connected to -3. Now let's try to look at A, okay? If you look at A, it says 6 is connected to -7. It doesn't collide with the fact that this got to be a function. But hey, I want you to look at B. We have a problem. We do have a problem. If you look at B, it says 3 somehow got to go from, not just -1, but it may go to -2. So what is the major difference between like a function and relation? And why does it matter? Like, why do we keep saying that this is a problem? Well, function must be a trustworthy machine. Gotta be a machine. Trustworthy. Let me write it down. Trustworthy machine. Why do we care about the trustworthiness? Well, think about it this way. I have 4 quarters, or let's say I have 5 quarters. I went to the vending machine and I plug Coca-Cola. And what if Sprite comes out? Because the Sprite has exactly the same price, right? And the $1.25 or that 5 quarters may actually go to the Sprite or Coke or Diet Coke or, something else like root beer and so on. But if I wanted to have Coca-Cola, except I got Sprite. Is that a trustworthy machine? No, it's not a trustworthy machine, right? So in that case, if we have one input that is, somehow assigned to multiple outputs, we no longer have that as a function. We have that as a relation. And relation, I'm not saying that this is not a trustworthy relation, but as a function, as a trustworthy machine, we don't trust it as much as we do for a machine, for a function. So this is question number 1, part 1. All right, so since we have to, maintain the function property, we must say that one input goes to one output. But what if multiple inputs go to one output? That's fine. That's fine. It only has one output. Think about it this way. If you have 5 quarters, put it in a vending machine, it gives Diet Coke. If I put, like 4 quarters and I plug the Diet Coke, it just still gives me Diet Coke. It's just a vending machine that gives Diet Cokes only. Does that make sense? So as long as we have one output that is that has been assigned from multiple inputs, that's still fine. Now, question number 2. It has a word, okay? Domain and range. Now, what is domain? Domain is the set of x values, all right? The set of inputs. We call it set of inputs. We only count it once, even though it may appear multiple times, or it may not appear multiple times. We just call it set of inputs as, the particular case. And we got set of outputs. The actual outputs, not the possible outputs. All right, so let's have a look at these questions. All right. We need to find number one. Should I write it in the following form? Yes. Number one, if I have to figure out using this, definition of what we got, domain must be counted only once. We have 1, 2, -2, 3, and 4. We're only counting the values that appear in the positions of x. And since this is a set, this is a collection of numbers, we don't have any orders attached, but normally we write it from the smallest to biggest, all right? So in our questions, the answer must be C. How about range though, all right? How about range? Just, for curiosity, let's try to also look at range. And even for range, we only write down numbers that appeared multiple times only once, all right? So check this out. 2 must be written. And 1 must be written once, and -1. So we got -1, 1, and 2. That must be the range. Making sense? Cool. So that's up to question number 2. Let us move on to, like a basic function notations, right? Here's a theme that I want to say. Don't panic. Now, normally when we say f of x equals 3x squared plus 4, and I'm talking about kids who are, weak at math. They usually say, oh, I need to plug x in the parentheses, so I only know about the rule for x, not 2x plus 1. So here's a game changer, a way to think about, in a different perspective. If we have f of something, think about a circular blurb, okay? If I have f of something that goes inside the parentheses, this is pretty much 3 times that circular blurb squared plus 4, okay? That's the meaning of it, okay? Now, if I have f of 2x plus 1, it's fine. All I gotta do is to consider that 2x plus 1 as a circular blurb. All I gotta do is to consider that as a circular blurb. And by considering that as a circular blurb, hey, we get f of 2x plus 1 equals 3 times 2x plus 1 squared plus 4. 3 times 4x squared plus 4x plus 1 plus 4. Making senses? Of course. 12x squared plus 12x plus 3 plus 4. So we got 12x squared plus 12x plus 7. And it is a quadratics, that's fine, but it doesn't even resemble anything about 2x plus 1, but hey, don't panic. Always consider that as a singular blurb, okay? Always consider that as a singular blurb, and you got to consider that as a blurb, as an input, the whole input. All right, so that's question number 3. It says, don't panic, right? Now, that being said, let's move on to question number 4. This is nice. This is a nice thing about something called, compositional functions. This is a new thing. Hi everyone, welcome back. Let's begin with quadratic functions. This is going to be the new start of, it's still a common part between the Algebra 1 and Algebra 2. But I think in this section, it starts to deviate from what we've learned in Algebra 1. So quadratic functions, the most important part about the function is how to graph, right? Now, there are 2 things that you need to remember. The first thing is that we have something called the axes of symmetry. Now, axes of symmetry never actually appeared in previous functions, especially in Algebra 1, in linear functions, but quadratic functions contain something called axes of symmetry, or some people call it as line of symmetry. And that line of symmetry can be given by a times x minus h squared plus k, which is known as the vertex form. So that actually tells us about an important process known as vertex, okay? Now, starting from the vertex, we have to understand the basic, or I guess the standard form of a quadratic functions, especially given by y equals x squared. That's a common, I guess the most commonplace parabola that you can see. The shape of the graph is definitely parabola. It's not linear, it's nonlinear. And we need to start from the vertex, which is going to be either the lowest point or the maximum point. Now we're going to start with the lowest point possible, okay? If we have some, like a point called vertex, now the next thing that we learn, or next thing that we use in that, that we've learned in Algebra 1 is going to be shift 1 unit to the right and 1 unit to the up, right? 1 unit right and 1 unit up. And unlike the linear function, this is going to change. The change of y is going to change. If I move 1 unit to the right once more, I'm going to go up by 3 units, okay? And if I go 1 unit to the right once more, I'm going to go up by 5 more units. And what can you expect from the next, what's the next step that you need to see? The next step is going to be, it's not going to be 5. The change of y is going to be change of y is going to be 7, 9, 11, and so on. It keeps increasing and so on. So it's not linear function. It's just going to be a parabola. It's just going to be a curve that goes up, that spikes up to the right side, the northeast directions. And we can sketch the line of symmetry as in the form. Now, as you can see, the line of symmetry, what we're going to do is that imagine we put some, we paste some kind of, like a colored, what should I say? Like some kind of, like colored paste. And imagine we fold it along the line of symmetry. And as we fold it along the line of symmetry, we're going to have the other image that pops out right away. That is going to be the quadratic function. And in order to understand how things work, we first have to figure out where the vertex is going to be located at. And as soon as we focus, as soon as we got that vertex positions, we're going to shift it right to the 1 unit and up by 1 unit and right by 1 unit and 3 ups, and 1 unit and 5 ups and so on. So other than just like a regular, like the standard form ax squared plus bx plus c, this is known as a standard form. Now, the standard form doesn't really tell us anything about the given information, except that we have the one condition that a is not going to be 0, and we can change this into 2 parts, right? One is going to be a times x minus h squared plus k, which is known as the vertex form, and also we can change this into x minus r times x minus s, which is going to be the intercept form, and this has been introduced by François Vieta, a French mathematician, who's a modern father of trigonometry and algebra. So, this is going to be uber important, like super important in competition math, but this one is more important, I think, in GPA materials. So, we're going to learn all of these courses and, of course, some kind of applications of quadratic functions, especially the optimizations and some absolute value quadratics. But that's not in this lecture right now. In this particular lecture, in this particular clip, we're going to focus a lot on finding out the vertex and finding out the shape of the graph, just, trying to compare what has been done so far. All right, so let's try to look at number 1. Now, in order to understand number 1, first we got to write down what really happened here. Now, like in front of x squared, we have multiplied 1/2. That means we're going to cut our height by half, right? So number 1, my height has been halved. It has been halved, 1/2. So unlike, like going up by 1 unit, 3 units, and 5 units, and so on, unlike the original graph, it's going to go up by 0.5 units, and 1.5 units, and 2.5 units, and so on. So I think in our grids, because we don't want to, like have some kind of like a messy work, I just want to call 2 grids as 1. That's fine, right? So that's up to me, right? So I'm just going to call it 1, 2, 3, 4, and so on. And I can also have, 1, 2, 3, 4, 5, and so on. All right, so let's try to use the dashed curve just to indicate what actually happened to the original graph and try to draw the solid curve for y equals 1/2 x squared just to compare what has been done so far, right? So if I sketch the vertex, and obviously vertex is going to be located at 0, 0, because if you change this expressions, y is going to be 1/2 times x minus 0 squared plus 0. That has been done so far. So we know that 0, 0, the origin, must be the vertex. Now, just forget about the transform function. Just try to think about the original curve. Now, what has been done in here is that from the vertex, forget about the left side. Just, think about the right side. Now, if you think about the right side, we're shifting 1 unit to the right, or shifting 1 unit to the upside. Now, we're shifting 1 unit to the right, and we're shifting 3 units to the up. All right, so what has been done so far? So this was actually happening in the following. All right, so 1 unit and the other unit, right? 1 unit and 5 more units. Go up, hit it up. All right, so it's spiking up so fast. Should I sketch it with the dashed curve? Yes. Let's try to use the dashed line. So we've been sketching the dashed curve. That's not the function that we want. That's not the graph of functions that we have to draw. I just drew y equals x squared. All I got to do is to cut our height into half. Now, what really happened here is that instead of going up 2 grids in the first spot, I'm making it go up by one grid. So 1 grid has been gone, and still I'm going 2 grids to the right side. And instead of going up by 6 grids, I'm making it go up by 3 grids, which is going to be 1/2 or 1.5, right? In actual real life, in the scaled version, instead of going up by 3 units, I'm going up by 1.5 units. And if I go up, if I go right by 1 unit, which is going to be 2 grids in our case, now in the upper, the upper part, well, the portion that actually went up was like 5 units, which is going to be 10 grids. Now, instead of going up by 10 grids in our graph, I'm going to go up by 5 grids. So let's make it up by 5 grids. And that's it. That's super simple. Connect those dots. Connect the dots. Of course, it seems like it gets a little bit wider, but it's not the actual widening, transformation. It's all about shrinking the height, okay? So you may say that, the horizontal shrinking and the vertical, horizontal shrinking and vertical stretching, or horizontal stretching and vertical shrinking are the same processes, but they're not, right? We're changing the height. We're not changing the width. We haven't changed the width. We just simply change the height. Are we done? No, we're not done yet. What do we have to do? We got to look at the axis of symmetry. Hey, we got to look at the axis of symmetry. Now, what we're going to do is that we're going to reflect our portion of the solid curve about that particular vertical line. Now, if we reflected about that line, let's see what happened here. I need to plot the points that I know. I need to plot the points. Right? I need to plot those important points down here. And voila. And connect it. And just beautifully connect it. Just extend it a little bit. And we get the function, finally. This is going to be a little bit wider than the usual function. But hey, that wideness wasn't actually affected by the horizontal stretching. It was actually done by the vertical shrinking. Make sense? So that's number 1. Let's move on to number 2. Hi everyone, welcome back. Let's begin with new topic, which is going to be application of polynomials. Now, for the first lecture in this, for the first part of this lecture, especially for the subtopic, I would like to go over something about difference of cubes. So here's an annotation of you need to write it: difference of x cubed, or difference of, I guess, just cubes. We can write this down as a minus b times a squared plus ab plus b squared. And of course, a cubed plus b cubed can also turn into a plus b times a squared minus ab plus b squared. Of course, there are a few more things that you need to know. For competitions, all you have to know is these, these expressions as well. which is known as a plus b plus c times a squared plus b squared plus c squared minus a minus ab minus ab minus bc and minus ca. But again, this one, I shouldn't write like 3 dots down here. This one is more like a competition. But the expressions that I wrote down in each two expressions, in top 2 expressions are going to be something used a lot, and especially in GPA related material. So let's try to move on to part A directly and see how it works out. First off, you need to see that this is a indeed difference of cubes. And as we notice, that's going to be difference of cubes. And you can write this down as 2x minus 3 times 4x squared plus 6 times x plus 9. And we need to find the all real zeros and imaginary solutions. And of course, we break it down into 2 parts, right? As we break it down into 2 parts, that's a linear and that's a quadratic. And we know that x is going to be 3 over 2, except the second parentheses tells us that we need to somehow use the just quadratic formula. All right, so x equals 2a in the bottom part and negative v plus minus square root of b squared minus 4ac. And that's going to be 144. So negative 6 plus minus square root of negative 108 divided by 8. Notice that that's going to be negative 6 plus minus 6 root 3i, right, divided by 8. And we can further simplify this by negative 3 plus minus 3 squared of 3i divided by 4. Those are the imaginary solutions, right? 2 imaginary solutions. So you can check that there's 1 real with 2 imaginary solutions. And as we write 2 imaginary solutions, these are called conjugates. They are conjugates. They come in pairs all the time. Now, I want you to look at part B. This requires a application of difference of squares, right? So I'm going to write difference of squares. Not bad. It can be written down in the following form, like this. Yeah. It must be x minus square root of 10 times x plus square root of 10, x minus 1, and x plus 1. So x is going to be square root of 10, negative square root of 10, 1, and negative 1. 4 real solutions. Okay, so that's part B and part A of question number 1. Let me just double check whether I didn't make any computational mistake, because I don't want to come back to this question again. There's 36 minus 36 and 444. Yeah, I think that's what's up. All right, so let's move on to the second question. Number 2, question number 2. All right. Solve for x. Not bad. We have to use all of the knowledge that we know. And when we say solve for x, it didn't mean that it got to be real or complex. So the best thing that we need to do is to find out all possible solutions, either real or complex, and let the teachers decide what to choose, okay? So that must be a application of difference of squares. You can see that that must be x squared plus 4 times x squared minus 1 equaling 0. Do we stop here? No. We can actually move a little bit further than this. I want you to highlight the first one. When we have the sum of squares, and especially if we allow complex solutions, we can actually further crack this. We can actually separate this into the product of two linear forms by making it down as x plus 2i and x minus 2i. And you can also change this into x minus 1 and x plus 1 equaling 0. We have two complex roots and two real roots. We have x equals plus minus 2i. We have x equals plus minus 1. Let me give you some of, like bits of annotations down here. Underneath part A, here's annotation as well. So if you look at the previous questions, we also had a quadratic functions. We had 4 real solutions, right? If we have degree, if you have degree 3, if you have degree 4, we might actually get few possibilities. 4 real and 2 real, 2 complex. And there could be 4 complex. And let's erase those possibilities. So we might have those 3 possibilities for degree 3. As you see, for each step, the number of complex roots get increased by 2 at a time. The reason why that happens is because if you look at all the coefficients are all real numbers. Now, if we don't have the real coefficients, that means this might be broken apart. But as long as we have integer the integer coefficients or rational coefficients and the nice looking coefficients as in these examples, we're going to have we're going to have this situation, or we're going to have this phenomenon keep, appearing all the times. It's going to keep appearing. And we have to understand that this is true because of the conjugates. The conjugates always come out in pairs. And as conjugates come out in pairs, out of 4 reals, we turn into 2 real and 2 complex. As you see from these examples, those 2 values that we found in the first parentheses are going to be complex roots. They come out in pairs because it must be 0 plus 2i, 0 minus 2i. We have those 2 expressions that come out at a time. And plus 1 and negative 1, they're not, we don't call them as conjugate pairs, but you can call them as a conjugate pairs, but that's true because of the difference of squares, okay? All right, so that being said, let's try to move on to part B. What's the rule that we need to know when we solve some cubic equations or polynomials? The best thing that we need to perform without doing such any expression whatsoever, without doing anything to the given expressions, we first have to factorize. If you see a common factor, you always need to factorize. Let's try to factor this. As you factorize these examples, we have 2 times x cubed minus 125 equaling 0. And as you see, that 2 can be crossed out. This 2 can be crossed out because it doesn't actually contribute anything to the solutions that we're looking at. Now, if you look at the expressions that are sitting inside the parentheses, notice that that is a difference of cubes. Yes? So it must be x minus 5 times x squared plus 5x plus 25. And obviously in the second part, the second parentheses, that must have no real solution. Hi everyone, welcome back. Let's begin with exponential function today. Now, exponential function, it's one of the transcendental functions. Now, what is an exponential function? It is usually having the form of y equals a times b of x plus c. So it's unlike the polynomial functions like radical functions and rational functions. The special thing about this is that the variable is going to be placed on the exponent. Now that's, that being said, we have a very weird concepts. I would like to move on to something about the change of y and change of x. Now, if you go on to change of x and change of y, I usually use this tactic also in pre-calculus. Change of x is going to be, it's just going to be positive but this is going to be multiplication. Interesting, right? Interesting. If I can give you a certain example down here. Y equals 2 to the power of x. Now, if I have y equals 2 to the power of x, and by the way, I wrote this down, y equals 2 to the power of x in the booklet, and you will have a copy of the graph of it. Now, when we sketch the exponential function, the most important thing that you need to remember is that we always start at 0, 1. We always start with the 0, 1, and that's the key point. This line segment, the unit line segment that is, like standing up, is going to be where we begin. Okay. Now, from now on, when we have to transform the function, we're gonna shift this left and right. We're gonna shift it up and down. But this segment is going to be where we begin. Okay. So as I move 1 unit to the right, if I move 1 unit to the right, I'm going to multiply my height, the original height, by twice, because that's 2. I'm going to multiply my height. I'm going to multiply by my height, multiply my height by 2. So it becomes 2. If I go 1 unit further, and I'm going to multiply my original height by 2 as well. And if I go 1 unit to the right once more, I'm going to multiply my original height by just like, it just keeps going on. So you can see that the graph, it's going to be going up. It's called exponentially growing. But we don't stop here. Maybe we could have actually looked at the previous step, or how the previous step looks like. If you look at -1, we have half of it. Whoa. Because we need to halve it, we need to make it half, because if you multiply that 1/2 of the length twice, then we get the length of 1. And we also get, 1/4. So it gets like shrunk and shrunk and shrunk, but that segment will never ever going to be what? 0. It will never ever going to be 0. So an interesting thing happens. We have the horizontal asymptote. We have the horizontal asymptote. And this is going to be the horizontal asymptote. Okay? So we have the exponential function that goes up. But we can also make sure that we can multiply by y equals, 1/2 to the x. And by the way, there are certain tactics that we need to know, that b, or the certain conditions that we need to always remember, that b is going to be always a real number that is positive. But we distinguish between like something that is positive and something that is like, still positive into 2 subcategories. We have something that is smaller than 1, something that is greater than 1. So we might have b greater than 0, but still smaller than 1, or we might have b greater than 1. We might have those 2 possibilities. And if we have something that is, like a fraction, a pure fraction between 0 and 1, we call this decreasing function. The function is going to be decreasing. And you can see that why that's true if you look at y equals 1/2 to the power x. But this one is obviously increasing, right? This is going to be obviously increasing. Why? Because it's going up. It has the upper going trend. So having said that, that's going to be the exponential function. We would like to look at some basic functions and like how to sketch basic functions, and then move on to some like analysis of exponential expressions and whatnot. Okay. Right. So having said this, I would like to go on to sketching, y equals 2 to the power of x minus 1 plus 1. Right. So we have y equals 2 to the power of x. That's the original function. And we would like to shift it right by 1. Right by 1. And up by 1. All right. Where is the constant segment? Where is the beginning point? The beginning point was 0 and 1, 0 and 1, right? I want you to shift that unit 1 unit to the right and 1 unit up. So we're going to have a picture that looks like this. Okay? Don't, just don't panic here. All you have to do is just to draw the horizontal asymptote. Imagine that's the ground. That's a new ground. That's the horizontal asymptote from now on. Horizontal asymptote is going to be y equals 1. Right. I want you to circle this 2. And that 2 is going to help us how to graph it. If I move 1 unit to the right side, then I'm going to multiply my previous height by this unit down here. It's going to be 2. So I multiply my height. I multiply my height by 2 units. I'm going to multiply my height by 2, and multiply my height by additional 2, and so on. Like this. We're going to multiply my height by half. Multiply my height by 1/2. 1/2. So as you can notice, the graph is going to be really close to the particular graph, really close to y equals 1, and except it goes like spiking up. It goes spiking up, as in the form. Can we analyze this graph? Of course we can analyze this graph. What is the, like a basic analysis of this graph? Analysis of this graph is that number 1, we have a domain. Now, domain is going to be the set of all real numbers. Who cares about the domain for exponential function? It eats everything. It takes in everything, right? But the range is going to be a little bit different, right? The range, as you can notice, is going to be a little bit different. Range is going to be something that is above y equals 1. So something that is above y equals 1. And you can also notice, you can also write this thing as an interval notation. Y is going to be stuck between 1 and infinity. And by the way, domain is going to be the set of all real numbers. If you want to write this thing as the interval notation, hey, that's how you do it. Right? So this is how we sketch the graph of exponential function using the multiplication rule. Remember this thing, right? Remember that we have always the segment, the vertical segment of length 1. We start from there, and as we move to the right side, we always multiply by the unit that you're looking at in the base, so that it becomes that fold times, that it's being multiplied at that number. It's being multiplied by that particular number as we move to the right side. It's a unit movement. As I move 1 unit to the right, it's going to be multiplied by that particular length. If I go to the 2 units to the right, I'm going to multiply 2 squared that unit. And imagine that's 1 and that's 4, right? If I go from 1 to, if I move 3 units, it's going to be 1 and 8. Make sense? Easy as pie, right? So that's question number 1. Not that bad, right? Not that bad. Exponential is not that bad. Of course, we haven't justified, the exact picture or how it is being derived from something else. It is derived from the geometric sum of all the polynomials that you can imagine, but we're not gonna, go on to that level unless we move on to calculus. Now, number 2 is going to be an exponential function that has the same form, y equals 3 to the power of x minus. I want you to sketch a graph in the empty space. I know that you have an empty space down here, of course, in your booklet. I want you to have x and y axes. And now we're gonna analyze the shape of the graph and see how it works out, right? So we always begin with 0 and 1, right? We always begin with 0 and 1. We always begin with 0 and 1. Hi everyone, welcome back. Let's begin with chapter 11. Which starts talking about counting, permutation, and combination. Now, when we talk about counting, we have to first figure out what's the basic tools, right? There are lots of tools that we need to learn. And the first tools that I want to talk about is one-to-one correspondence. So that's the first set of tools. And the second tool that I need to talk about is whether we know how to multiply or add or multiply. Do we know when to multiply, when to add? And this makes it this produces 2 sets of consequences. We have casework, and we have complementary counting. complementary counting. And the next set of tools that we have is something called recurrence. Recurrence. Now, recurrence relation is not part of this Algebra 2. It's in fact, it will come out in competition level math. And even in my, like the introductory course, recurrence is not part of it because recurrence is part of the high level competition. It does come out when we cannot use casework and complements and direct computations using combinations and, like all the other tools. If we can't use that, then we use the recurrence formula. But anyway, those are the major tools that we're going to use. And of course, like we can classify some of the countings in 4 major types, which will not cover, we won't cover this. We won't cover the 4 major types of something about permutation allowing repetition, combination allowing repetitions, and partition of natural numbers and partition of sets. Those are covered in the introductory course of the competition math. Now, that being said, let me talk about one-to-one correspondence, which is something that is, familiar with. Why? Because one-to-one correspondence uses everything that we know. One-to-one correspondence uses the multiplication, division, addition, and subtraction, and sometimes the square root thingy, and so on. So, as long as we have those rules, for an instance, if I give you 1, 2, 3, 4, and 5, this has a one-to-one correspondence between 2, 4, 6, 8, and 10. Why? Because this is exactly same as multiplying by 2 to each number. Does that make sense? So that's going to be one-to-one correspondence, and I will go on to question number 1 to tell you what's going on and how to use those questions and the set of tools, the basic tool of one-to-one correspondence. Now, we're basically counting. When we say counting numbers, that refers to sometimes, the set of natural numbers, or sometimes the whole numbers. Just either way, we use those numbers. And I'll show you the basic drill of how to do it, okay? So there's a solution number 1. Solution number 1 uses the fact that we are going to find one-to-one correspondence. Like this. Yes. So after writing down all the list of the numbers, I want you to look at the common difference is just 1, right? So what we're going to do is that we're going to divide this. Oh no, we're not going to even divide this. We're going to subtract equal number. We're going to subtract 55 from the top to bottom. We have 1, 2, 3, 4, ... If you subtract 55 here, we get 118, and we get 119. We have exactly one-to-one correspondence between the first number to first number, second number to second number, the third number to third number, and so on, all the way down here. So in order to find out the number of numbers or number of integers on the top list, we can use the number of integers in the bottom list. So we have 119 numbers in total. Now, what about solution number 2? Solution number 2 uses different stuff. Okay, solution number 2 uses certain, like formula. If I need to find out from A to B, the total number of integers stuck between A to B is going to be B minus A plus 1. And by the way, the common difference got to be just always 1, okay? We have 174 minus 56 plus 1. We have 175 minus 56. We get 119. Okay? So that's solution number 1 and 2 for question number 1. Got it. But what's a better solution, out of these two solutions? This is obviously better. Solution number 1 is way much better than solution number 2. Why? Because solution number 1 uses the general tool of one-to-one correspondence. This is more specific to a very special set of numbers. But anyway, let's go on to number 2, okay?
find the number of even integers. Got it. So we have even integers. We cannot use solution number 2. We need to use one-to-one correspondence. One-to-one correspondence. So how do we tackle this? 2, 4, 6, 8, ... all the way to 432. Okay? Now, you see the common difference between the two, it's just going to be 2. Yes? This is going to be 2. That's just going to be 2, and so on. Right. So if you divide this by 2, you get 1, 2, 3, 4, and ... all the way to 216. You see, after dividing it by 2, we automatically get the number of integers in the bottom and number of integers on the top, which has the one-to-one correspondence between each number, respective numbers. So the number of integers in the top list is going to be exactly equal to the number of integers in the bottom list. We have 216 numbers. Make sense? Got it. So that's one-to-one correspondence, and now we shall move on to, why we multiply, why we add, and so on. Right. So let me write down a few stuff. Multiplication principle. And when we talk about multiplication principles, we have to classify when we multiply or when we add. We need to know why we're doing it, Like, when do we do this? Number 1 and number 2. We multiply things if you feel that the action or the number of counting is not done yet. So I usually call this as action is ongoing. So we're not done with the counts, the full amount. So think about this way. Define the number of ways that you can eat breakfast and lunch. Like eating breakfast, you need to choose the number of menus for breakfast. Let's suppose we have 4 menus. You choose one of them. So you have 4 choices to, choose the meal for the breakfast. And are you done yet? Well, gotta think, right? We're not done yet. Why? Because you gotta think about the way you need to eat, you need to choose the meal for the lunch. Since you're not done with the counts, you need to multiply by the number of menus that you have for the lunch. Anyway, number 2, when we usually say the structure is exactly equal. Structure is repeated. Now, like when we add, this is more like a casework. When we need to perform casework. In other words, things cannot happen at the same time. Okay. And number 2, structure is being repeated. Structure is not repeated. So here's a common rule that I usually show you. Let's suppose we have a guy in the, select shop for apparels, right? He can choose 4 shirts. And let's suppose he can choose 5 pants. And a clerk asks the customer to go inside the closet or...
Hello everyone, welcome back. Let's begin with new topic, probability, which is an extension. This is an extension of counting. So as long as you remember counting properly, we can solve a lot of the questions. And I'll teach you the principle of probability, especially multiplication and, just like addition and whatnot. But there are so many things that we need to know about probability. First, it deals with something called sample space. And I'll deal with sample space as well. And when we cover probability, you have to remember 2 things. Even though it doesn't seem distinct, we call it distinct. Consider them distinct. Consider distinct elements. So what I'm saying is that even though we throw 2 equal coins at the same time, you can always consider them all distinct. Now, if we are looking at the outputs, wow, got to think about the outputs carefully too. Outputs, if we have same kinds or not, distinct kinds, here's the distinction. If we have equal kinds or same kinds, do not multiply by the number of different configurations. Do not multiply by different configuration. However, you need to multiply by different configurations. By configurations. And I'll show you what that is, okay? I'll show you what that is as we move on to question. And I hope to finish this, this particular clip, this lecture, this one right now, around like question number 6 or 5, okay? So let's try to move on to question number 1. Gotta be thinking carefully. When it says the Bob is planning to flip a fair coin 3 times, is it at the same time? Or, is it at the same time? Or in a row, the answer gotta be same. So if you think about a probability carefully, people always get confused about the fact that we need to throw it at once. We need to throw die at once. We need to throw multiple dice at once. But in math, when we say at the same time, it means that it has to happen consecutive manners. So in other words, eating breakfast and lunch in math, it's also at the same time. Because after you eat breakfast, you have to spend about a few hours just to digest stuff and do some other activities, right? Before noon, right? And then you eat lunch. As soon as you eat lunch, then in math, we call them eating breakfast and lunch. But also it's pretty similar to then, right? In math, and then can be used, kind of interchangeably, except then kind of requires something called conditional probability. So other than just like that particular conditional probability, all of the things are pretty much the same. So check this out. If I need to flip a coin, I need to have 2 number of possible cases for the first coin. Is my count done yet? No, my count is not done yet. You need to flip another coin, the second coin. And is my count done yet? No, my count is not done yet. I need to flip another coin. And there we go. There we go. That's the sample size. But I didn't write down the sample space. And it says the sample space consists of all possible events. The size of the sample space. This is called the size of the sample space. Of the sample space. And you can consider sample space as a universe, There's no other thing that you can produce out of this, sample space. Right, so having said this, let's try to write down the sample space. There could be H, head, head, head. There could be head, head, tail. There could be head, tail, head. There could be tail, head, head. There could be head, tail, tail. It could be tail, head, tail. It could be tail, tail, head. Or it could be tail, tail, tail. I wrote down all 4 cases. Now, because people are so confused about the fact, about the at the same time, people usually say, oh, there's an overcount. Well, I gave you all 8 possible cases, but somehow, not dumb kids, but what should I say? Some confused kid will say, oh, you overcounted because, hey, that's a 3 head, and this is all 2 heads, and this is 1 head, and this is no head. Well, that's a good try for categorizations, but again, you should consider all of them distinct. But sir, I don't get it. If you throw at the same time, if you throw 3 coins at the same time, even though there's head on my right, even though there's a head on the left, shouldn't I consider them all, equal? Because we have 2 head and 1 tail after all, right? No. I'm telling you that when we deal with probability, we have to match up when we throw it in a row. So what I'm saying is that day number 1, you throw coin 1, you got head. Good for you. Day number 2, you throw another coin, you got head. Good for you. Day number 3, you throw a coin, you got tail. Well, is that equal to day number 1, you throw coin, you got tail. Day number 2, you got you got to throw a coin, you got head. Day number 3, you get head. Are they equal? Don't you think that they are different? They are different. They are distinct. That's why we call them 1, 1, 1, 1, 1. Then if that argument, if one of the confused students or one of your confused peers, if you have that confusion right now, saying that, don't we have to get that 4 possibilities? Then that should have been 4 too. The size of the sample space gotta be 4, but it wasn't. It's 8. So there must be some kind of confusion between your analysis, your understanding, and whatnot. So here's the major deal. If you get confused about the throwing at the same time, please throw it in a row, okay? Throw it in different days. That's fine. We have to get the same answer. We have to get the same. That's a rule for probability. If you don't want to follow the rule for probability, then don't study this. And if you don't study this, don't go to awesome colleges. That's what it is, right? This is Algebra 2, guys. Come on, come on, come on. We can handle this. We can handle this. Because, like in my offline class, when I was young, there was a kid who actually bugged me of this. Who keeps insisting that, we need a sample space, that sample space got to consist of 4 things. And I told her, no, we got to consist of 8 things. And she didn't understand. So out of 2-hour lesson, I had to argue with her for 2.5 hours, even though my class was 2 hours, but we argued for 2.5. I don't know why this is an argument. I don't see why this got to be an argument. But apparently, I just, I told the hagwon at the time that I'm not going to do the class with her anymore. So that was the first and last class for me, with her. Apparently, she went to some college. I don't know. I don't care which college she went to, right? Come on. Let's go. Mr. Know-It-All rolls 2 fair dice. Do you have to roll it at the same time? No. Do you have to roll it in a row? No. It's just up to you, please. If you understand that throwing a die at a time and throwing at a die, throwing 2 dice at the same time, if that's not confusing to you, just follow whatever you want to do. Okay? Now, Mr. Know-It-All rolls 2 fair dice. What is the probability that the sum will be 6 or less? You throw 1 die. You throw another die. We have 6 and 6. It's a multiplication. It's a permutation allowing repetition. We throw 2 dice, 2 distinct dice, and we get the first dice, the second. Right. I wanted to have the sum of the numbers will be 6 or less. So what if my sum equals to 6? Then can it be something like 5 and 1? Can it be something like 4 and 2? And can it be something like 3 and 3? Can it be something like 2 and 4? Can it be something like 1?